When two or more waves combine in space, interference phenomena occurs. Like we see in this picture, interference phenomena is visible by two different sources creating a wave. So the total wave at any point at any instant of time has a displacement equal the sum of the instantaneous displacement of individual waves at that point at that time. This is called principle of superposition, and this principle is the most important principle in all physical optics. Physical optics studies all the optical effects that depends on the wave nature of light, and this principle is valid also for electromagnetic waves. Such an optical effects we also observe from surfaces of soap bubbles and, for example, DVDs. How is it possible for colorless objects to produce these remarkable multicolored reflections? Interference is easily seen with sinusoidal waves, which are characteristics of monochromatic light. Monochromatic, which means mono means single, chromatic means a color, or single frequency light. So common sources of light do not emit monochromatic light. The most nearly monochromatic source that is available is the laser, and for example, helium neon laser, which emits red light at 632.8 nanometers plus minus 0.000001 nanometers. Now, in order for interference to happen, there are two conditions. One, the sources must be coherent. That is, maintain constant phase with respect to each other. And two, the sources must be monochromatic, or which is should be single wavelength. Now consider two monochromatic light sources, S1 and S2. The two sources produce waves of the same amplitude and the same wavelength, and they are permanently in phase. Now, to better discuss or analyze this, I'm going to bring a picture that I have created in a different place, where the circles are kind of better than I drew. So this one is my source 2, and the top one is the source 1. I drew here x and y coordinates so that the sources S1 and S2 are on the y-axis, and the perpendicular line through the middle of the distance between S1 and S2 is the x-axis. Now let's consider a point A on the x-axis, which is, from the symmetry, we know that the distance from point A, from source 1 to point A and source 2 to point A, these distances should equal to each other. There are 5 wavefronts that meet each other from each source at point A, which means they will require equal time to arrive to that point A. Hence, waves that leave S1 and S2 in phase arrive to point A in phase. So, and the total amplitude at point A is twice the amplitude of each individual waves. So amplitude at A equals amplitude from source 1 plus amplitude of the wave source 2, and we initially said that they have similar equal amplitudes. That will make it 2A. Now if we take a look at the distance from source 1 to point B, that is this distance, which makes it 1, 2, 3, 4, 5 wavelengths, and from source 2 it will make 1, 2, 3, 4, 5, 6, 7 wavelengths. That is exactly 2 wavelengths greater than the distance from S1 to B, point B. So wave crests from S1 arrives at B exactly 2 cycles earlier. So in general, when 2 waves arrive at a point in phase, then they reinforce each other, and this is called constructive interference. Now something different happens when at the point C, when waves arrive to point C from S1 and point C from source 2. As you can see from S1, the wavefront, there are 6 wavelengths, 6 lambda, and from S2 the path length is a 7.5 wavelengths, which is 1.5 wavelengths away. This means that 2 waves arrive at point C at exactly half a cycle out of phase. Crest of one wave meets trough of another wave. So the resultant amplitude will be 0. So if I put amplitude at C, it should equal the positive amplitude from S1 minus plus negative amplitude from S2, which will make it a 0. So when the waves cancel each other out, this is called a destructive interference. So for the case of a constructive interference, we had the path from source 1 to point B, R1 equals 5 lambda, and for the path of from S2, source 2 to point B equals 7 lambda. So the condition, we wanted the phase, to arrive to point B in phase, which they do. So I would say R2 minus R1 equals 7 lambda minus 5 lambda, which equals 2 wavelength. So the condition in general case for constructive interference would be the path length of from the second source to the point, and a path length from the first source to that point, to particular point, should equal integer number of wavelengths, where the m is equal to 0, plus minus 1, plus minus 2, and so on. For the case of destructive interference, so R1 equals 6 lambda, R2 equals 7.5 lambda, and the path difference between the source and the point where we're interested in, R2 minus R1 equals 7.5 lambda minus 6 lambda, which makes it 1.5 lambda. So the condition for destructive interference in a general case would be R2 minus R1 equals m plus 1/2 lambda, where the m is an integer number, 0 plus 1/2, plus minus 1 plus minus 2, and so on. Going back to our soap bubble, the colors that you see in this bubble is totally due to the constructive interference of light, where the soap bubble can be considered a very thin spherical film that is filled with air. So when the light is reflected from the outer and inner surfaces of this thin film of soapy water, interferes constructively to produce the bright colors. Well, which color we see at any point depends on the thickness of the soapy water of the film at that point, and also on the viewing angle. So stay tuned for more on the thin film interference to come. Thanks for watching.